Ever wonder what makes a Big Mac bun the Big Mac bun? Perfectly soft, slightly elastic, yet strong enough to hold a hot, saucy sandwich without falling apart. It's not nostalgia, it's not branding, and it's definitely not magic. What you're biting into is the result of decades of food engineering, starch chemistry, and industrial precision designed so that a bun behaves the same way in Tokyo, New York, or Manila. And once you understand how it works, you'll never look at a burger bun the same way again. Before we break this down, if you enjoy uncovering the hidden engineering behind everyday things, food systems, and the technology we take for granted, subscribe to the channel. These stories take time to research, and your support helps keep this series going. Now, let's talk about the most overlooked component of fast food. The fast food bun looks simple: flour, water, yeast, sugar. But in reality, it is one of the most demanding components in the entire fast food system. A bun must be soft, but not fragile, elastic, but not chewy, moist, but never soggy, and it needs to maintain its structural stability under heat, steam, and pressure. It has to survive grills, toasters, steam cabinets, delivery boxes, and impatient hands-all without tearing, collapsing, or drying out. Most importantly, it must do this millions of times a day with near-zero variation. This isn't artisanal baking. This is high-stakes food engineering. When people think about bread structure, they usually think about gluten. But in fast food buns, starch is the real hero. Starch makes up nearly 70% of flour, and it comes in two forms: amylose, which forms firm gels, and amylopectin, which creates softness and elasticity. The ratio between these two determines whether a bun feels fluffy, rubbery, or dry. During baking, starch granules absorb water and swell in a process called gelatinization. This is the exact moment when dough stops being dough and becomes bread. Fast food buns are engineered so this process happens at a specific temperature for a precise duration with controlled moisture. Too much gelatinization, and the bun becomes gummy. Too little, and it crumbles. Getting this balance right isn't cooking, it's applied chemistry. Unlike traditional bread, fast food buns are designed for performance over flavor. To achieve that, food scientists use modified starches to improve water retention, emulsifiers to stabilize fat and moisture, and enzymes to control softness over time. These ingredients slow down staling, the process where starch molecules realign and push out moisture. That's why a fast food bun stays soft for hours, sometimes even days, without falling apart. The bun isn't meant to be impressive on its own. It's meant to be predictable. In food science, there's a term most consumers never hear: dough rheology. Rheology is the study of how materials deform under stress, and fast food dough is under constant stress. During mixing, engineers carefully control the mixing speed, time, and temperature. This determines how gluten and starch interact to create a dough that stretches without tearing. Industrial mixers don't aim for feel. They aim for measurable elasticity. Tested using rheometers and tensile analysis. Then comes proofing, where humidity, airflow, and time are controlled down to the minute. Every variable exists for one reason, so the bun behaves exactly the same on every assembly line. Once the dough is ready, there is no room for human inconsistency. Automated systems divide the dough to the gram, shape buns with uniform surface tension, and align them perfectly for baking. Even small variations in size can cause uneven baking, which affects starch gelatinization and moisture retention. At this scale, precision isn't just about efficiency, it's survival. Industrial ovens are not oversized kitchen ovens. They are thermal engineering systems. Inside these massive ovens, heat is applied in zones. Airflow is engineered for even energy transfer, and steam is injected at precise moments. Early heat triggers starch gelatinization, mid-zone heat sets the structure, and the later zones control crust formation without drying out the interior. The goal is not taste. The goal is structural repeatability. Once baked, buns are rapidly cooled to stop moisture loss and prevent the starch from oversetting. Even the cooling process is meticulously engineered. But here's the real challenge: humidity, wheat variety, and water mineral content all change depending on the location. Yet a fast food bun must feel identical worldwide. To achieve this, companies use rheological testing labs, sensory panels calibrated to texture instead of flavor, and constant formulation adjustments. If humidity rises, the hydration ratios change. If the flour protein shifts, the starch behavior is rebalanced. This is not baking, it's systems engineering. The next generation of buns is already being developed. Trends include enzyme-driven softness with fewer additives, sustainable starch sources, and AI-assisted quality control that replaces human testers. But the goal remains the same: perfect consistency at a massive scale with minimal waste. The fast food bun isn't simple because it lacks complexity. It's simple because its complexity has been hidden. Behind every soft, resilient bun is chemistry, engineering, automation, and decades of optimization, working quietly so you never have to think about it. And that may be the greatest engineering achievement of all. Thanks for watching.